So, as I was saying in my last lecture, that nonlinear optics comes into play when you have shorter and shorter pulses, because you get high peak powers and high intensities. Okay. And general medium is starts behaving completely in a different way. Usually the optical property of a medium is independent of the electric field amplitude. Electric field, I say electric field here because the laser light or the light is associated with an electric field. Okay. Everything will be in terms of that electric field. So, so if I have a laser wave here, so I have a laser or any light wave, I have an associated electric field. Okay. So, this is the electric field. Now, this is the electric field which creates havoc in the medium and gives rise to this nonlinear phenomena in optics. Okay. So, the electric field amplitude of the propagating light wave, okay, as I have shown here, but large power densities matter behaves in a nonlinear fashion. And we come across many new nonlinear optical phenomena like second harmonic generation. Okay. Second harmonic generation, I mean you've put in a frequency in your medium as omega, and what comes out is 2 omega. Okay. So, the frequency has doubled here. So, this is called second harmonic generation. Okay. Then the intensity dependent refractive index. As your intensity changes, the refractive index of the medium changes. That does not happen when in a normal light which we are passing through isotropic material or from or any material, glass or whatever, or liquid. It has a usual laws of Snell's law, etc., will apply, which are all linear optics. But the moment that intensity of that light is high, all those laws can be thrown out into the wind. Okay. You have to understand the behavior in a different way, and new laws have to be formulated. Okay. Then you have something like mixing frequencies. Mixing frequencies is same as almost the same as harmonic generation here. Okay. It is similar. In mixing, you just have say omega 1 plus omega 2. When your input is, you give omega 1 and omega 2, you will get a new frequency of omega 1 plus omega 2. That is called mixing. Then you have Kerr lens effect, Kerr effect, which gives rise to the Kerr lens mode locking. So, again another way of mode locking that happens, it is called Kerr lens mode locking. Only after you understand this phenomena of Kerr effect, then only I will describe this this kind of mode locking behavior. Okay. So, this is in addition to saturable absorber, etc. Okay. In a linear medium, the electric polarization P is assumed to be a linear function of the electric field E. You know this. Okay. Okay, and it is described as P is equal to epsilon 0 chi E. You have come across this formula in electrodynamics many times. So, the polarization happens because there is an electric field, and because there is a light incident on the medium, there is an electric field associated with it, and so there is a polarization also that is taking place in the medium. And chi is the linear dielectric susceptibility. So, it is a linear effect. Okay. You have an electric field, you have a polarization, and chi is a linear dielectric susceptibility. Epsilon, as you know, is the permittivity comes in. Okay. So, this is linear, it is still linear. Okay. It is still linear optics. But at high optical intensities, that correspond to high electric fields. Okay. So, your electric field becomes larger and larger as you go to higher intensities. Okay. The field value, the amplitude of the electric field associated with that particular frequency or with that particular wave of light, okay, becomes more and more. Once that amplitude becomes more, P no longer remains linear. There has to be some nonlinear effect in it. So, P becomes epsilon 0 chi E. This term corresponds to just these, the linear effect. And but then you have a whole lot of other effects which are nonlinear. The moment you have E square, that's nonlinear, E cube, the properties of matter goes on becoming new and something different because of this intensity. E square gives you intensity, this is E cube, which intensity into E, and so it goes on. So, this part is the nonlinear part of the polarization, and this part is the linear part of the polarization. So, at high intensities, your polarization it composes of two elements. One is the linear part and one is the nonlinear part. Now, let us see what is this nonlinear part. Chi 2, chi 3 and other higher order susceptibilities give rise to the nonlinear terms. Okay. This chi 2, chi 3, chi 2, chi 3, there is chi 4, chi 5 and higher orders also. So, we will limit ourselves to chi 2 and chi 3 because most of the interesting effects take place within this. At higher and higher orders, this chi 2, chi 3, chi 4 is smaller than chi 3, chi 5 is smaller than chi 4, and so it goes on. So, this becomes smaller and a smaller value comes into being, okay, and they can be neglected, and nothing much happens in the medium because of that. So, most of the properties of the medium that is changed and very interesting properties come in this chi 2 and chi 3. So, chi 2 will give rise to second harmonic generation, some frequency generation, which is this omega 1 plus omega 2, difference frequency generation, it will be omega 1 minus omega 2 generation, and then parametric interactions and so on. These are some of the things, and we will cover these. It is easy to cover this. And then we have the chi 3 effect, chi 3, that the third order polarization, that third harmonic generation is possible. That means you will get frequency, if you have input frequency of W omega, you will get 3 omega, okay. Third harmonic generation, intensity dependent refractive index, okay. So, here I have spoken about intensity dependent refractive index. It happens because of chi 3. It is a third order phenomenon, not a second order phenomena, but a third order phenomena. Self phase modulation is also a third order phenomena, and 4-wave mixing is also a third order phenomena. And these happen, and chi 2 do not happen at that time. When this is happening, this is not happening. I will explain why that is so. Okay. Now, before I explain all that, I think we should understand what is the physical origin of nonlinear polarization. Okay, why do we need to bother about this nonlinear polarization? Just to get a feel of what it is, we must know what is the physical origin of it. So, this happens because outer loosely bound valency electrons in a crystal or in a liquid or any material gets an induced dipole moment, and P, the capital P polarization, is dipole moment per unit volume. So, because of that induced dipole moment, what induces it? The electric field of the light induces it. So, you get this dipole moment, and all this is happening with the loosely bound valency electron. and there is a displacement of charge from the nucleus, okay. And that gives rise to this optical polarization of the dielectric crystal. So, I will just give a more pictorial structure: induced dipole moment and optical polarization. So, suppose all these are they may be atoms or even small molecules. The center one is the nucleus, okay. Here is the nucleus, and then the electrons are moving around this. It is just depicted in terms of this ellipse, perpendicular and horizontal ellipse. And these are kind of bonds. The atoms are stuck together in bonds like this, covalent bonds or whatever, they are all bonds here. Now, what happens is, it's just an array of atoms linked by chemical bonds, okay. So, E is what is inducing this polarization, what is the driving force. It will not happen if it is if that crystal lattice is just sitting there, nothing will happen. There has to be a driving field. So, I will call E as the driving field, which is an external field. In our case, the external field comes from a ray of laser light, and the relationship between the electric field and the dipole moment is non-local in space. Okay, why do I say this? Suppose I have an electric field here, okay, it is going here and it is localized in this position, and all these electrons here, these loosely bound electrons or the electrons between these two bonds here, they are obviously affected by this electric field, and they try to move away from the nucleus, or they vibrate in a larger ellipse. So, there is a shift from the nucleus, and this negative charge is here. It is shifted out from its equilibrium position. It can easily be done with this electric field, and that induces a dipole moment. You have positive on one side and negative on the other. So, you have made this sort of a structure. You have made that, and you have induced the dipole moment, and per unit volume you will get capital P, okay. Here P is the dipole moment per unit volume. P, so I have put it in a very localized place. The beam of light is just coming through somewhere here. It gives the electric field, and this is what it does to the outer electrons and then further to the material. Now, it is localized, this electric field, because your beam is very narrow. So, it has created a sort of a dipole moment here, a disturbance in the electron field, and that thing has sort of an effect even on this. Suppose the electrons are moved away here, obviously these electrons will also get repelled and move away. These electrons also will get repelled and move away. So, the electric field may not directly affect that, but it definitely affects that in a secondary way, okay. And so directly it will affect the electrons here, here and here and here, and subsequently all the other parts also get affected, because of this charge separation. All of them start moving in some direction or the other. So, P, the dipole moment, has a character of a tensor. It is localized here, the E, but really it has affected the dielectric response in all these parts also. So, P has a tensor, it is a tensor character, okay. Now, what I want to say is when how high should be the electric field in order to get this kind of a response in the polarization P. Generally, the large electric fields encountered in practice are around 10 to the power 6 volts per centimeter. I just assume they are quite large fields, okay. and most forms of matter will exhibit electrical breakdown for fields which are higher than 10 to the power 6 volts per centimeter. Okay. So, what do I mean by electrical breakdown? By electrical breakdown, you already know all these electrons that are displaced actually. When the electric field is so large that these loosely bound electrons are have left this nucleus completely. So, you have stream of electrons moving about here and there. They are no longer in the influence of this of the nucleus, and then breakdown occurs, and physically what we know is there will be short circuits, or there will be damage in the crystals, or yeah, it is almost like a permanent thing. And these short circuits are very common in many places, and they damage your whole apparatus. Okay. But non-linearity does not really require those high fields of 10 to the power 6 volts per centimeter. It will occur much before that. So, the nonlinear part, the nonlinear optical response will happen much before an electrical breakdown in a dielectric system, or in a crystal structure, or in a glass structure, wherever. It will be much before this electrical breakdown. You do not need even 10 to the power 6 volts per centimeter in order to achieve the nonlinearities that you actually see. So, to give you some examples, just as a comparison, just to give you a feel of what I mean by induced dipole moment, what I mean by breakdown, and what I mean by optical polarization, just to give you a feel of that, it is good to see the dielectric strengths and electrical breakdown points of a few medium. So, first thing is the perfect vacuum I have just taken. Perfect vacuum breaks down at 10 to the power 10 megavolt per centimeter, megavolt. So, here this is 10 to the power 6 volts. So, 1 megavolt, this is 10 to the power 10 megavolt per centimeter. So, perfect vacuum is a very good insulator. Air somewhat has, air obviously is the breakdown point is at a much lesser electric field. So, it is at 0.03 megavolt per centimeter. Fused quartz is 0.08 megavolt per centimeter. And KTP crystal, which we use very often in lasers to get second harmonic generation, that is why I have put in this example, is 10 to the power 5 volts per centimeter. So, it will break down if I go above 10 to the power 5 volts per centimeter. But all the nonlinear effects in KTP will happen much before this value. Okay. So, this is just to tell you where breakdown occurs and where the nonlinear effects happen. Now, I should know what is the electric field associated with a laser beam. How much electric field can I generate with a laser beam? Okay. I should be able to calculate that, and then only the comparison will be complete. So, what is the electric field of a laser beam? Electromagnetic wave. It can be related to the intensity. Now, see, all these nonlinearities are happening because of the high intensity. Okay. So, what is the electric field associated with a high intense pulse? E is given by 8 pi I by C. This is the formula. You can look it up. Just believe me, this is the formula. Okay. So, that 8 pi and all that, if you take it out, so you have 27.5 root of I. If you give the I intensity in terms of watts per centimeter square, then you will get electric field in terms of volts per centimeter, and that is what we want in order to make a comparison here. So, for say intensity of 50 gigawatts per centimeter square, which can be easily available from a carbon dioxide laser, a pulse carbon dioxide laser, the electric field associated with a beam of carbon dioxide laser in 10.06 micrometer will be 61.49 into 10 to the power 5 volts per centimeter. So, all you have to do is put that I value here and take the root of it, and you will come to this value. So, it is about 10 to the power 5 volts per centimeter, which is much less than this value, 10 to the power 6 volts per centimeter, and you will get all the nonlinear effects by that. So, if you have an intense carbon dioxide laser pulse, which is in the 50 gigawatt per centimeter square range, and how do you get this? You can compress the pulse or focus the pulse at in a certain point. Suppose you do not have such a large energy initially, you can always focus it and get it to this high intensity. You see, it is per centimeter square intensity. So, if you focus it, you are making a smaller and smaller area, and your intensity is going up there. So, these units are very important. Okay. Now for, say, suppose I take another intensity, maybe for ND glass. I think this is an example of ND glass. You can get 10 gigawatt per centimeter square intensity very easily from ND glass, and the electric field would be 8.69 into 10 to the power 5 volts per centimeter square. So, all these lasers give you pretty high electric fields. Okay. They will not cause the breakdown, as I have given you some values in the yellow colored box, while it will not give that, but it will cause a disruption in the medium as far as induced dipole moment goes, as far as the dipole moment per unit volume goes, and that itself gives you newer and newer optical phenomena. And that is what I want to address. What are these newer optical phenomena, newer and interesting optical phenomena? Okay. So, here actually I have just so that you again understand what that polarization versus optical field means in a linear dielectric and a nonlinear dielectric. So, this part and this part corresponds to linear response of the dielectric or medium, crystal, glass or whatever, and this part is a non-linear response. So, just to give you a pictorial idea of the polarization versus optical field. So, this is the optical field, this curve, the tall one here. Okay. So, when it is linear, when the P, capital P is proportional to E only. Okay. Only E. So, that means the polarization sort of follows E, maybe some amplitude part may be less, so here, but it follows the same frequency, because the driving force is the E for this P. This is the driving force, driving electric field. So, it nicely follows the electric field, and the frequency also of that polarization is the same as that of the light which is incident, okay, on this field. So, here if you see the difference A and B, I have just given a difference, this much difference, that is the same difference here. This is the polarization line, this is the optical field line. So, you just see this difference in amplitude is same, nothing is changing over time as it goes on. Another way of representation is this. Suppose this is the electric field and this is the polarization. It is kind of a straight line, it is a linear response. Electric field increases, polarization also increase here. When it is negative electric field, okay, polarization also here is just this much, here it is this much. It just depends on the electric field. Electric field is here and here. So, A, this is A, this dashed line is A, which I have represented here, and this line is B here, which I have represented here. So, they are identical, I mean they are equal. Okay. So, not much of a difference. Now, what will happen when I have a nonlinear response? So, the nonlinear response, now P is no longer proportional to E, but P is proportional to E plus P nonlinear, or P is proportional to E plus E square plus E cube plus, and so it goes on. Okay. So, that you have seen previously. Now, what happens? What happens? So, I put in a frequency, my light frequency is like this, its amplitude is a little more than this, the previous one, okay, because it is at a higher amplitude of E only that you will start getting the nonlinear optical effect. So, this is the optical field, and the green part is the polarization. So, just notice this, when there is a positive electric field, the positive part of the lasing part, you have this much difference between polarization and E at the center, you have this much difference. But at this negative part, the polarization also has increased, the difference is very small, here the difference is very small. So, this part of your electric field induces only that much of polarization, but this part induces a much larger polarization. So, just like here, suppose I were to depict it here, it is no longer a linear function, polarization is no longer a linear function of electric field here, like here. There is a bend, you know, it need not be a bend like this, it can be a bend anyhow, you know, it could even be something like this or something like this, anything other than linear. Okay. So, this is just to show that it is no longer linear like this. So, my electric field is quite high, but my polarization may not be that high, it is this A and B. So, I have given this A and B. A is for the electric field and B is for the polarization. So, here is a polarization. But here if you see, the electric field is this much, which is the same as here, but the polarization has increased. You see this line, it is much more than this. Okay. So, this is just to show in two different, just to illustrate how P, the polarization, becomes non-linear in structure. So, we will go through all the effects that I have shown previously, all the second harmonic generation, intensity dependent refractive index, and mixing of frequencies, Kerr-Lenz mode locking, and many such phenomena. I will go through them, and you will see that there are some very surprising phenomena, and laser cannot, you know, the lasing field cannot be complete without knowing the nonlinear response of material brought in by the laser field itself.